Welcome back to BE 110. Today we'll do some examples of strain fields and flow patterns using the tools that we've derived over the last week or so. So let's consider the example of plane strain. You'll remember we did plane stress. Well, there's an analogous definition of a plane two-dimensional strain situation, and that's one in which the deformed coordinates little x1 are only functions of the original coordinates big X1 and big X2. Similarly, little x2 are only functions of big X1 and big X2, and little x3 is equal to big X3, or optionally plus a constant, which would just be a rigid body translation, three direction. And so this would result in a deformation gradient tensor FIR with components F11, F12, 0, F21, F22, 0, and then 0, 0, 1. And then using that to calculate the strain, we would get strain components ERS that were only in the first and second rows and columns, where the third row and the third column would all be 0. So that's the definition of plane strain, and you get the same pattern for the Almancy or Cauchy strain tensor definitions. This next example of pure torsion is most easily done in cylindrical polar coordinates. So imagine we have a cylindrical bar, or it could be a tube here, with constant radius and length shown here as L torque. Subject some torque or twisting moment to it with a moment arm of L twist and a force F external. And the result is that holding this end fixed, that this end would twist or rotate through theta degrees. And every plane along the length here would twist a little bit less in proportion to the distance along the length, so that the twisting angle is a constant in proportion to the length. And we'll call that constant alpha, which would be this theta divided by this L torque. And you see that that's the only thing that happens. The radius doesn't change, the length doesn't change. There's just a circumferential displacement that increases proportionately as we move along the length from z equals 0 here to z equals L torque. So calling the twist per unit length alpha and writing the displacements in polar coordinates, then the deformed radius will just equal the undeformed radius. Deformed theta will equal undeformed theta plus an increment proportional to the z coordinate times the constant alpha, and then deformed z will equal undeformed z. So to go further, we need to be able to write the deformation gradient tensor in cylindrical polar coordinates. In other words, where our deformed coordinates, instead of being little x, y, z, are little r, theta, z, and our undeformed coordinates are capital R, capital theta, capital Z. So the deformation gradient tensor would no longer just be partial derivatives, and in fact the proper definition in polar coordinates of the grad of x, where the capital G indicates partial derivatives with, or a gradient with respect to undeformed coordinates, would look like this, where the components FIR would be del little r, del big R, just as you'd expect. But then instead of del little r, del theta, an element of length in the circumferential direction is r d theta, so this is 1 over big R del little r del theta, then del r del z. Then similarly, instead of being del theta del r here, it's r del theta del r, because an element of length is r d theta. Then r d little theta over big R d big theta, r d theta dz, dz dr, 1 over r dz, d capital theta, d little d, z, d big Z. So you can see the only difference here is that wherever there was a d theta, there's an r associated with it, and that's because an element of length in the circumferential direction isn't d theta, it's r d theta in polar coordinates. And so then applying this to the displacements that we've defined, then del r is 1, and del r, del theta, and z is 0. Del theta, del r is 0. Del theta is 1, but we have an r upon r here. And then del theta, del z is alpha, and there's an r here, so we get r alpha. Then del z is 1, and del z, del r, and theta is 0. So now we have the deformation gradient for this problem, and we can proceed from that to compute the components of the strain tensors and the right and left Cauchy-Green deformation tensors in the same way that we did before. This next example is more of a proof or exercise, and the exercise is to prove that if a line segment stretches by a certain stretch ratio lambda such that it is deformed from an undeformed length of delta capital L to a deformed length of delta little l, so that del little l equals lambda del big L, where del big L is the undeformed length. The problem is to show that lambda squared is equal to AR times AS del XI del XR del XI del XS, and you might recognize that latter term as C, the right Cauchy-Green deformation tensor, or in vector and tensor notation this would be A transpose C A, where A here is the unit vector in the direction of the undeformed line segment delta with length delta L. Okay, so to prove this, let's first define delta X in the deformed state, which would therefore be delta L, which is the magnitude of that element, times A, which is the unit vector, and then delta big X to be delta big L times capital A. Little a and capital A could be different because the segment could have rotated. So that would then say that delta L by little a must equal F by delta L times big A, because that's the definition of the deformation gradient tensor. Now, using the fact that the stretch ratio lambda is delta little l over delta big L, then we can rewrite this expression as lambda A equals F by A, or in index notation, lambda A sub I equals dxi del xs times AS. Next, we square both sides, which gives us lambda squared AI, or A dot A, which would therefore equal FIR times AR times FIS times AS, where FIR and FIS are del XI, del XR, and del XI, del XS. Now, AI times AI, since A is a unit vector, will be 1, so that gives us lambda squared equals AR times AS del XI, del XR, del XI, del XS, which is what we wanted, or writing this in terms of the deformation gradient tensor, that's A transpose F transpose FA, which is therefore A transpose CA, which is the result we were looking for. This next example is a rigid body rotation, but it's a rigid body rotation at a constant angular speed, omega, about the origin. So if omega is the angular speed, then the velocity vector, v, would be omega times the vector that's the cross product of the unit normal defining the axis of rotation and the position vector x. Now, expressing this in index notation would be vi equals eijk, the permutation symbol, times omega times nj xk. Now recall the vorticity vector. W is equal to the curl of the velocity vector, which in this case would be omega times the curl of n cross v. And that, it can be shown, is equal to 2 omega times n. Rather than just have you accept that, let's actually do the proof by writing this in index notation. So Wi would therefore be omega times, using the permutation symbol, del xq of ejkp nk xp. Now you might want to stop and take a look at that for a moment to make sure that we've used the permutation symbol correctly. But generally when we take the cross product of two vectors, then the index of the first vector will be the second index of the permutation symbol, the index of the second vector will be the third index of the permutation symbol, and then the first index will be the component of the new vector that this product is a result of. So similarly with the curl, you see we have I, Q, J. The Q refers to the derivative operator, and then the J refers to the component of this new vector n cross v. And then the I would be the components of the resulting vector, which we've defined to be W after multiplying by omega. So then rearranging that, we would get omega times EIQJ EJKP times NK. Since the unit normal is a constant, its derivative doesn't come into play, and then we get del xp del xq, but that is just the Kronecker delta pq. So now we have omega EIQJ EJKP NK delta pq. Now we'll use the E delta identity, which will convert EIQJ EJKP into delta Ki delta PQ minus delta KQ delta PI times delta PQ from here times NK. Now simplifying this by using delta PQ to convert this Q to a P, and this Q to a P will become omega delta Ki delta PP minus delta Kp delta Pi times Nk. Now delta Pp is 3, so that will be 3 delta Ki minus delta Pi turns the P into an I, so this is minus delta Ki times Nk. So now we have omega times 3 minus delta Ki, which is delta Ki, so we get 2 omega Nk delta Ki, and then finally delta Ki converts the K to an I, so we get 2 omega Ni. So Wi equals 2 omega Ni, or in vector notation, W equals 2 omega N. Okay. So that's the vorticity vector. We can also compute the velocity gradient tensor Lik as del Vi del xk, which would therefore be del xk of the original expression we wrote, which is Eijk omega Nj xk. And since the only non-constant in here is xk, del Vi del xk is just Eijk times omega times Nj. Now if we look at this expression, we realize that Eijk is 0 whenever I is equal to k. So therefore the diagonals of Lik will always be 0. So what about when I is not equal to k? Well, then in that case we note that Eijk would be the negative of Ekij, because that changes the permutation, which would mean that Lik must equal negative Lki. In other words, what we've seen here is that the velocity gradient tensor is in fact a skew symmetric tensor, which means that in this example of a rigid body rotation, then the velocity gradient tensor is the spin tensor W, and the rate of deformation tensor is equal to 0. So this is informative because it tells us that in general, if the flow contains a rigid body rotation, then that will appear in W. And so therefore, the decomposition of L into a spin tensor and a rate of deformation tensor effectively separates the velocity gradients into rigid body rotations and components that are not rigid body rotations that actually reflect flows. And so D is the part of L of the velocity gradients that doesn't include rigid body rotations. Similarly, in the same way that U and V, when we did the polar decomposition theorem, were the parts of the deformation gradient that didn't include rotations. So the example we just did is a rigid body rotation, but it's not a vortex. That's because in a vortex, the speed of rotation gets faster and faster as you get towards the center. So we could write a velocity vector field with this flow property by making v1 proportional to x2 divided by x1 squared plus x2 squared, which would be like the square of the radius, and v2 proportional to x1, also divided by the radius squared, which means that the magnitude of the velocity will increase in inverse proportion to the radius. In this example, v3 is 0, so the rotation, the vortex here is about the origin, about the x3 axis. Turns out for this flow, surprisingly, that the spin tensor is actually 0, and in this case the rate of deformation is 2k1 x1 x2 divided by x1 squared plus x2 squared all squared. So again, that's d1 and minus d11 and minus d22, and then there's a shear component d12, which is k times x2 squared minus x1 squared divided by x1 squared plus x2 squared all squared. So the symmetry decomposition of the velocity gradients into spin and rate of deformation has the effect of separating out rigid body rotations, but don't confuse a rigid body rotation with a vortex, because in a vortex flow you actually have a gradient of velocity as you go from the inside to the outside. You also get a singularity, though mathematically, at the origin at x1 and x2 is equal to 0, and that turns out to be a pure rate of deformation without any rigid body rotation component.